Now we'll turn to conservation of energy using a similar approach as before. Remember that the first law of thermodynamics states that the increase of the total energy in a material or fluid parcel volume is the sum of heat transferred and the work done on the particular volume. We'll denote Q by the heat flux and capital E by the specific internal energy in this case. Sometimes I like to use little e, but here we'll use big E. We can then find the balance expressed by the first law as equation 157 directly. And we've shown this before, so we won't recover its approach again a second time. But just look at the terms. The left-hand side is the rate of change of the energy, specific internal energy and kinetic energy within the fluid parcel. The right-hand side represents the heat transfer, body forces, and viscous terms as we talked about before. The first on the right-hand side, remember, is the rate at which the body forces do work, and the second term represents the work done by the stresses, respectively. The third is the heat flux into the volume. We can expand this equation using the theorem of stress means. In particular, write F equals U of I and arrange the terms through the use of the transport theorem of Cauchy we previously developed, and we'll have 158 in an expanded form. It's nice to write the equation this way because we can see that the rate of change of kinetic energy is the material volume. In the material volume is the sum of three parts: the rate at which body forces do work, the rate at which internal stresses do work, and the rate at which surface stresses do work, respectively. Through the use of the transport theorem and Green's theorem of George Green, we'll find the following equation 159 in a compact form. This is the dyadic term. That means that we'll take Tji of Uji and it'll result in a scalar term, which is a product, of course, of the stress and nabla U. So we can write this more compactly as rho times the material derivative of the internal energy is negative nabla dot Q, remember heat transfer, plus the dyadic of T and nabla U. We can then use Fourier law to rewrite the first term on the right-hand side as nabla dot K nabla theta, and here this theta will indicate temperature, so we don't confuse it with the stress. This is named after Joseph Fourier, who is a French mathematician, and here's a nice history slide on him.